The second part of the problem says to show that the shearing component of the traction on any of the 8 octahedral planes is equal to the shearing component squared equals 1 over 9 times sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. Using the relationship between the shearing component, the normal component, and the magnitude of the traction, you get the equation: the shearing component squared is equal to the magnitude of the traction squared minus the normal component squared. So to find the magnitude of the traction, you get it from part 1, which we found to be the sum from 1 to 3 of plus or minus sigma j over the square root of 3 times nj. And that magnitude is equal to 1 over 3 times the sum of the components times the sum of the principal values each squared. So to get the normal component squared, we use the normal component is equal to the sum of the principal values over 3, and then we squared it to get this value. And then that eventually reduces down to 1/9 times this quantity. And then substituting back in for the magnitude squared of the traction minus the normal component, you end up with this equation for the shearing component squared, which reduces down to this, and eventually you'll get the shearing component squared is equal to 1 over 9 times sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 1 minus sigma 3 squared, which is what we were looking for.